So today I'm going to uh, talk about the double pendulum, and I'm going to demonstrate and show you a simulation. But first, I'd like to talk about the significance of uh, of this experiment. So one of the things that I talk about a lot is about how to predict the future or coming up with ways to predict the future. But how predictable is the future? And there are different kinds of things. Some of them are easier to predict, some of them are not. So this demonstration will show how certain things, even very simple things, are not very easy to uh, predict. So there is something called as the dynamical systems. So in simple terms, things like anything that changes with time. Like for example, the movement of a car, like in class 11, 12 physics, we studied like the car is going, so the velocity changes with time, might be constant and so on. So things are changing with respect to time. So certain things are linear. For example, a car going at a maybe even if it's going at a constant speed or variable speed, we have these equations of motion. So those equations of motions make it completely deterministic. For example, like if you know the initial velocity, like if you remember, let me show you if there are some formulas. So here, this kind of equations we studied. Okay. Yeah. For example, this is like the final velocity. Velocity is equal to initial velocity plus acceleration times time. So if you want to know what's the final velocity after time t, so if you know the initial velocity, if you know the acceleration, if you just plug in and if and whatever time you want to know it, you can get the final velocity. So this is a completely deterministic system. You can definitely uh, know its future thing. But certain things are not determinable. For example, if you ask me, if someone asks you to predict what am I going to do 3 months from now at 12 p.m., what am I going to do? You can't predict. Even I can't predict what am I going to do at that time. So those things are indeterministic. But this is human behavior is quite complex. But there are certain very simple things. Even very simple things are harder to predict. So this is one of those. So let me just start with a simple one, and I'll go to the more complex ones. So this is what a double pendulum looks like. Mm. Okay. So as you can see, it is moving quite erratically. Like it doesn't seem to have any pattern. But that's not the most important thing. It for something to be predictable, it doesn't have to have a pattern. So in one, actually, the very interesting thing about this system is that it is a completely deterministic system, but it is not a system that can be predicted. Deterministic, but not predictable. So can you see some kind of contradictory statement here? A system that is deterministic, but it cannot be predicted. Yeah. So what does it mean? So basically, when I talked about dynamical system, what I meant was in simple words that things change with respect to time. Certain things are so if you like draw like classification diagram. So at top we have this dynamical system. So we can make two classification. First one is deterministic system. Second one would be random system. Or other some a more complicated word to define random is stochastic system, which is random. This thing is not random. It has an equation, And if you plug in the values, we can exactly know what exactly its position will be at certain amount of time. Just like the car, just like this equation. It has an equation, it is completely deterministic. But this system has a property known as sensitive dependence on initial conditions. So what does that mean? It means that, again, coming back to this equation. So in such this kind of linear simple equations, a certain small variation doesn't make a lot of difference. I can give you a very real world practical example. For example, if you go to office normally at 9 a.m. and it takes you 30 minutes to reach office. So if you start at 9 a.m., you'll reach at 9:30 a.m. But if you decide that, okay, I'll go at 9 a.m. and 8 seconds. So you'll reach office at 9:30 a.m. and 8 seconds. It's not going to be like if you are go at 9 a.m., 8 seconds, I'll reach at 11 a.m. It's not. It's very simple. Whatever delay you have while leaving, that will be the amount of delay you'll have while arriving. So 8 seconds of delay doesn't make any difference. This is quite small. So this kind of linear systems, small changes like a small variation doesn't make any difference. But this is a non-linear system. Here, even a very small change can make a lot of difference. Lot in the sense that it is completely unrecognizable. I'll show you a different one where I'll have two and I'll assimilate both of them at the same time. Let's see which one was it. Was it 5? Yes. And also there will be another graph here. You may ignore it or you may also view this one. So this is basically the plot of the values of angle 1 and angle 2. So angle 1 and angle 2 is simply uh, if you okay, let me show you the so this is the angle 1 and this is the angle 2. So the angle that the first pendulum makes with the vertical axis, that's angle 1, and the angle that the second pendulum makes with the vertical axis is angle 2. So this will only simply be showing that one. That doesn't matter. Now I'll show you. And I said that even a small change can make a lot of difference. Right now, I'm going to make both of them same. So these are the, I think I know it's black, so it's very hard to understand, but maybe if I do this. So there will be two different pendulums. For now, I have kept the angles of the top angle and the bottom angle of the first pendulum and the top angle and the bottom angle of the second pendulum same. So they will move exactly the same. In fact, you'll only see one color. I think so. You'll only see blue. You won't see red, or maybe you'll see red. You won't see blue because it will be what's it called overlapping on top of each other. So this is the simulation. Let me change start speed up the process. Okay. You can only see one line actually. There is a red one as well, but you
Which
won't
line are you
not
talking
able.
about?
This whole thing that's going on here.
You're saying there's two pendulum, like
Yeah,
four
actually,
pendulum, two double pendulum.
yes, but you are only seeing one because they are all
Yeah.
both of them are moving at the same thing, same one. But now if you see, these are the angles. These are these initial angles. Now suppose if I change the angle, for the second pendulum, I change it to be something different. Suppose I'll make it 9 and I'll make it 12. So now the changes, the initial angles in which they both will start are very different now. Now let's see how it looks like. Okay. Now this is obvious, like if the angles are very high, so their behavior will be completely different. Now if I can, let me see if I can duplicate it. Let this thing keep going on. And now the same thing, let me show you here. Now what I'm going to do here is that you can see the top, I'm going to change only the final, the fourth decimal place. So they're almost equal. Fourth decimal place is insignificant in lot of real life events. As I've said, like leaving your home for office at 9 a.m. or 8 seconds later doesn't make any significant difference. But you'll see how sensitively dependent it is on initial conditions. On the fourth decimal place I have changed. It's the others are almost exactly the same. Only the bottom angle I have changed at the fourth decimal level. And let's see how it moves. I hope. Yep. And you can see. Now I'll show you how chaotic it looks. And this. Now if I hide the angles and if I show two people, like tell me which one has a very high difference in angles and which one has only a difference in the fourth decimal place. By looking at it, people won't be able to tell. So the practical implication here is that certain things are, even though they're deterministic, for example, if you plug in the actual values, we can find out what it will look at the future. But the real world constraint is that we have there will be errors in measurement. And even a tiny bit of error will make this prediction like valueless. Like it will be so different, it won't even matter. Like your prediction will go way over, means way off. One real world example is weather. So that's what it is exactly the same as this thing. It is uh, also a non-linear system. So a tiny change, a tiny change in the number, the initial values will give you wildly different values of what the weather might be. So the thing is that even the most advanced models in weather prediction, weather forecasting, can't forecast beyond a certain amount of time because of such kind of things. But again, at the same time, you'll see a kind of pattern appearing here, which is actually obvious because once its speed goes down, it all comes down towards the bottom.
But I don't clearly still understand the difference. Why is it deterministic yet unpredictable? So what about the system is deterministic and what about it is unpredictable?
Okay, so deterministic means it is defined by an equation.
The movement of the pendulum is defined by an equation.
Equation which is deterministic. Suppose for that, in the same ways, let I double penetration. Let me see if there is an equation here. Yes, this is the equation. So suppose I want to I think this represents that position. But anyways, what the point here is that if I want to say, suppose at time t equals to some, suppose I want to know that, suppose after 1 hour, where exactly will be the mass, suppose this is the mass 2, where exactly will be the position of M2 after 3 hours if I continuously run this simulation, and I want to know where exactly will be the position of M2 after 3 hours of continuously running this simulation. And if I plug the values here and the value of time wherever it can be plugged, I don't think this is the actual equation, but whatever the actual equation is, we can exactly point out the position of that uh, mass 2 at time equal to 3 hours. In the same way, we can determine the final velocity of a car. If you know the initial velocity, if you know the acceleration, and suppose we want to know after t equal to 3 hours where that car will be, we can exactly predict this one. So this is what a deterministic means. The opposite of deterministic is stochastic or random process. So in random process, there is no equation. So you cannot predict where exactly that system will be. Like this is not a example of a random system, but if suppose there is a random pendulum, no pendulums are actually random, but let's assume there's a random pendulum. So there you won't be able to predict like, okay, after 3 hours or after 1 hour 37 seconds, where exactly will the pendulum be? In a random system, you won't be able to predict. But as I've said, in deterministic system, there are two kinds of uh, subsystems. You can make further division. One is a linear system and one is a non-linear system. Double pendulums are example of non-linear system. And one of the properties here is that, as I've said, it has sensitive dependence on initial conditions. So if I want to predict this, I want to, I need to have the exact initial values. For example, I use some device to measure the initial angles. But suppose the device that it has certain limits of accuracy. For example, you know those weighing machines. So suppose the ones we used to weigh ourselves. So that's fair enough. But if you in your school or maybe during engineering lab, I remember they had very precise weighing machines for, I think so it was in chemistry lab, I think. So if you want to some exact milligram of some chemical you want to take or some salt or something, so you can't use very generic ones. You need to have like accurate to the decimal places of milligrams. So those are very specific machines. So you need to have those kind of machines. But even those machines have certain kinds of inaccuracies. So the thing is that if you do not have the complete data of the initial conditions of the system, your prediction will go way off. And that is why it is not predictable because of real life constraints of the inefficiencies of the measuring systems.
So the initial, so it is unpredictable because of the lack of, let's say, incompetency to figure out the initial conditions. If we were able to very precisely understand the initial conditions, then the
Yes,
system is also predictable.
yes, it is predictable. But
But is it not
realistic,
possible at all?
I don't think so. It is possible because at least at the uh, I don't know, and I won't say quantum. In quantum physics, there is Heisenberg's uncertainty principle. You can simultaneously measure the position and the momentum at the same time. But I think that doesn't apply to this one. These are macroscopic systems. These are not uh, quantum systems. But at the same time, like realistically, like this is a pendulum. Still, you might be able to figure out something. But real world systems such as weather, how will you know what is the initial system of all the molecules in the planet? That is practically impossible. Of all the clouds in the planet, how can some machinery be used to calculate all the initial positions? And as I've said again, the term initial sensitive dependence on initial conditions. You can't like, okay, a little bit of approximation, we can just little bit of approximation, doesn't matter. Like in school, it is g equal to 9.8. No, you can take g equal to 10. Here you can see again the evidence. You can see 0.09, and what is the result? What you can see here. So and this is one of the most classic. This example is the hello world of nonlinear systems. Let's now compare hello world with a real world computer program, the difference in complexity. So this is one of the simplest systems, and even here we can see how much chaos it creates only due to a tiny error. So imagine what kind of chaos it will create when you're trying to predict the weather with inaccurate information, which is realistically not possible. But because for a long time people thought that, okay, even if it's not possible to take the exact value, we can approximate. And because s- for the most of the entire human history, what people thought was that people thought linearly, okay, a little bit of change doesn't make a lot of difference. As I've said, as I gave the example at the beginning, like 8 seconds of delay won't make a lot of difference. But then this is a very fairly recent field. I think maybe 50 to 70 years old since this kind of phenomena were discovered. That even a small bit of discrepancy makes a lot of difference. Now, let's see if there is some convergence in the pattern. There isn't. In a way, there is. I don't think so. There isn't. Now, this is obvious. Like once it goes down, it will keep fluctuating around the center here. Here it's a bit different. And there is another one that I wanted to show. This is actually the same in terms of the output is the same, but the way this is simulated is different. That's the only difference here. Uh, I'll have to make it run for a few minutes, then you'll be able to know the difference. So what happened here was that in these two is that its energy seems to have reduced in this and this one.
Mm.
So you can see it initially it was moving here a little bit, but now it's all just oscillating at the bottom. Almost similar here. It has a little bit of more energy. It's going up, but still, as you can see, the frequency, sort of like the heat map, it's mostly at the ground now, and that's why there is a lot of concentration of the angles within here and here. But the way this was simulated in this one is different. The energy does not dissipate. I think this is not realistic. It should not dissipate, but it seems like it is also dissipating here. Is it because of the small angles? So till now, do you have any other questions?
Mm, really, this is probably the first time I'm properly hearing about this concept.
Okay.
So this is exact. If it's a non-linear system, you said, right?
Yes.
So what are some more examples of linear and non-linear systems?
Okay. So first, let me talk about the definition. The definition is like for a linear system, the change is 1:1. It's simply in simple ways. You might have seen the linear graph y equal to mx plus c, like a straight line graph. In school, you have already seen a lot. So one unit change in the x-axis brings a similar amount of change in the y-axis. Like it's a linear kind of thing. What if, and a very simple example of a nonlinear is the quadratic equation y equal to mx square. It has this kind of graph. So if you change y by 1 unit, x will change by square of that unit. It won't change linearly. So this is a very simple example of a nonlinear system. But so in real life, I think very few things are actually linear, like in very controlled environments. One simple example of a nonlinear system, the very example that I gave in the beginning, like a 8-second delay won't matter much, but actually it might matter much. It might matter a lot. Suppose you have to catch a bus to get to your office, and it leaves, and if you miss that bus, you'll have to wait for 20 minutes for the next bus, and the bus leaves at exactly 9 a.m. So if you are 8 seconds late, you won't arrive office 8 seconds late. You will arrive office 20 minutes and 8 seconds late. So this is a very simple nonlinear system. So so once you know the definition, you can look at observe different kind of systems around around your daily life and be able to predict whether this is linear or non-linear. Because linear is 1:1 change, but a non-linear is not a 1:1 change. But at the same time, not all nonlinear systems are chaotic like this. Only certain kinds of nonlinear systems are chaotic. Like any simple quadratic equation is also not as chaotic as this. It is nonlinear, but it is also still both deterministic and predictable because y equals to x squared. It's very simple. Now, uh, let me show you one video which goes into this in far more details. Uh, Even I don't understand most of the videos. We have 10 minutes left, so we'll just briefly look at this. But the visuals of these videos are very good. So even if you don't understand, even I don't understand much of it, but you'll still be able to appreciate it.
Plotting the top angle as x and the bottom angle. Double pendulums are not chaotic, or at least not all of them.
Yeah, this is what also caught my mind. So far I've been telling that double pendulums are chaotic, but he says that it's not chaotic. Uh, I haven't figured out why it is not chaotic, but I assume it might be due to there might be certain initial starting angles. Like if you start with in at those angles, it might be still not chaotic. I'm not sure. I'm just
You've
just
probably
saying
seen
anything.
videos like these,
Just look at
where a
this.
tiny deviation in similar double pendulums amplifies over time until they completely desynchronize. This system is so sensitive to initial conditions that it's practically unpredictable, so we call it chaotic. But you probably haven't seen this. These pendulums also have slightly different starting positions, but they will not diverge. They even trace a repeating pattern, for which I call this the pretzel pendulum. A stark contrast with the first ones, which are making a complete mess. So what's the deal? These pendulums follow the same laws of physics. The only difference is the position from which they started, and behavior as a function of starting position can be graphed, revealing fractals like these, where each point shows how chaotic a certain pendulum is. But before diving into the fractals, let's get to know a few individual specimens. This pendulum is one of the chaotic ones. We are particularly interested in the angles that separate each bar from the vertical. Plotting the top angle as x and the bottom angle as y, we can make a graph like this. This pendulum is evidently chaotic from the graph. It follows no consistent pattern. Here's a non-chaotic pendulum. It's drawing a shape known as a Lissajous curve. Here's the signal from the top and bottom angles separated out. We can run this pendulum for a long time, reinterpret these signals as sound waves on the left and right speaker, and listen to the pendulum. It doesn't precisely sound beautiful, but compare that with the chaotic pendulum. And here's the pretzel pendulum. This one traces a repetitive curve in angle space, so it sounds the cleanest. Listening to a pendulum tells us if it's chaotic, but we have to listen one by one. Instead, we can make a large array of pendulums like this. The pendulum's x position in the grid corresponds to the top angle, and its y position corresponds to the bottom angle. By associating angle positions with colors, it's easier to tell what's going on. As a bonus, we can add points in angle space for these pendulums and see how they move. Let's increase the resolution to 1 pendulum per pixel. A nice feature of this fractal is that it tiles the plane. Rotating either pendulum arm by 2 pi yields the exact same position, so the fractal is periodic. Pay attention to how there are 2 distinct modes of behavior here. There's a region of chaotic pendulums sensitive to their initial conditions, as well as a region of coherent ones which are not. Now, for each pixel, we track 2 pendulums, separated by a slight starting difference, and plot their difference over time. So, this plot shows how quickly the pendulums in our grid diverge. Let's reset the pendulums and watch that again from the start. Here we go. Now, I'm going to pick a certain point corresponding to a pendulum in the black region, meaning its behavior is non-chaotic. We can plot its path in angle space just like we did before. Moving the point around in the black region, this curve moves smoothly and cleanly. This main black region is home to all the Lissajous style pendulums. But as soon as you leave and step into the chaotic region, all hell breaks loose. Let's look closer at the chaotic region in white. There are a few spots of black in here. These islands of stability contain special pendulums which follow stable paths. This big island of stability contains the pretzel we saw earlier. This one, which I call the shoelace, traces a more complex pattern.
Wait a minute, he's giving certain angle values. If I put those values, 2.658, we have 3 minutes left. No. 2.658 minus 2.19. Minus 2. It's not happening. But what I understand, what it's trying to say is that if for certain values of theta 1 and theta 2, the pattern it creates is repetitive. It keep repeating those kind of patterns. But for other values of theta 1 and theta 2, it is completely chaotic. So that's
Yeah,
what it's
but
trying to
I
say.
did not understand the reason why, or I don't know if you mentioned the reason why. I could not
No,
understand.
I don't think so far he hasn't mentioned the reason why, but he only has talked about this.
This one draws a picture of a heart. This island is particularly small. We've seen how the pendulums, which start near the angle 0, 0, are very well behaved. Those pendulums have extremely low mechanical energy. So
There's only 1.5 minutes left, so I'll just summarize so far what I've understand, and I'm quite sure I'll continue this next week. So this graph, what is showing here is that x and y values, these are x and y values of theta 1 and theta 2. And wherever there is black, and if we take any value of like what is called any coordinate within this black, and if you plug it in, the pendulum will behave in some kind of uniform kind of motion, repetitive pattern. But if we take any values from any white section, then it will move in a completely not random but chaotic ways, because it's not random because it is deterministic. So that is what I've understood. So I think this week I'll try to see whether if I put certain values, it produces some kind of pattern or not. And I'll try, and if it does, I'll also try to understand why it does, and for some values, and why it doesn't for some values. And next week I'll discuss more about that. Okay, so it will be over.